Okay, again, written exam of February 21, a continuous beam, concrete beam, reinforced concrete beam, spanning two spans. They have different length. So this is L, this is 2L, and also different bending stiffness. So here we have EJ, and here we have 2EJ. The second span is loaded by a distributed load. Magnitude is P, small p. I usually adopt small letters to indicate distributed loads and capital letters to indicate concentrated loads. That's my convention, just to make it clear. So the request was, considering the statically undetermined reinforced concrete beam shown in the picture. So the text pretty much clarified from the beginning that it was a statically undetermined beam. Solve the structure by means of the set of coefficients provided separately. We will recall the relevant coefficients as we need them. Determine the restraint forces at the three supports, where it was specified that A is a hinge, B is a roller, and C is a roller. The letters obviously are A, B, and C. And the third request concerning structural analysis is plot the diagrams of the internal forces and give a qualitative sketch of the deformed shape. Pretty much like I did the last time. As I did last time, I would like somebody to come to the blackboard and, without writing down one single number, sketch the deformed shape which will guide us in the solution, okay? No grades at stake. Come and show me whether you understood. A bit more accurate as you have the diagram of the bending moment, but surely we know one thing that we should expect. Here there is clearly a curvature which is like this, which means that to have such a curvature, we need what we call a negative bending moment. So we expect the first span to be subjected to a negative bending moment. Basically, it is bent like this. As for the second span, since the curvature looks like this, I expect the bending moment to be positive, okay? Which means tension is at the bottom. Never mind too much about the signs. When I say positive and negative, that's again is a convention. One way we use to describe what the bending moment looks like. But most important thing is you know where the tension is. And since such a curvature is generated if you have an elongation of the bottom and the shortening of the top, this means tension at the bottom, okay? So if we have a solution which does not comply in some way with this, we have to be careful. Clearly, since there can be no abrupt variations of the bending moment, remember what we said last time, unless there are applied bending moments, which you don't have here, the bending moment diagram should be continuous, okay? No jumps, okay? So there will be no abrupt change of sign in the bending moment from the first span to the second span. There will be a continuous transition from negative to positive. So either in the first span I will have some positive bending moment, or in the second span I will have at least a small portion of negative bending moment, okay? Let's not be surprised about that. But as you go on into the second span, you will have a positive bending moment, okay? To the solution. We know it was written in the text, the structure is statically undetermined. Again, this means equilibrium equations are not enough to solve the structure. You need to write compliance equations. Basically, if you write the equilibrium equations, look at the structure, it is basically one single beam. It has 1 and 2 reaction forces here because it's a hinge, 1 reaction force here because it's a roller, and another reaction force here because this again is a roller. So we have on the whole 4 reaction forces, 3 equilibrium equations. It's not enough. So we need to solve. And solve by means of compliance equations. Again, in this case, it is not feasible to split the structure as we did in statically determinate structures because it will lead nowhere. All this is a little bit useless if you recognize from the beginning that this is a continuous beam with some statically indeterminate reactions. Okay? How can you know how many unknowns you need to take to solve the structure? Well, basically, again, you can count, and counting is not a good idea in my opinion, although in this case it works. Or you can simply say, if I remove roller B, this becomes a statically determinate structure, so a simply supported beam. Since I had 1 restraint, I have 1 unknown, so 1 statical unknown force. Again, it can be external force, like reaction force, or internal force, and that's the way we usually solve it. Did you have a question? Oh, sorry, because I saw that. Okay. So what would the choice be? What would the most...
That's why was my answer. Change will be break the 2.
Yes, that's, I mean, it looks a little bit, it should be quite well understood by this time, okay? So what we usually do is we transform internal hinges which impose the same rotation to the left and to the right, we change them to full hinges, and therefore we introduce a kink in the rotation. And then the compliance equation is basically imposing that the rotation is again the same, to the left and to the right. So what I do to solve the structure is, this is the unknown internal force. Since it's an internal force, it has to be drawn to the left and to the right. Principle of action and reaction. Okay. Name capital X. No need to put a subscript because there is only 1 unknown. Okay? Tell me.
You don't count the degree of constraint and degree of freedom of each hinge?
Yes, that's basically what I did. When I said 1 continuous beam has 3 degrees of freedom, or I can write 3 equilibrium equations, and I have 4 reaction forces, it's the same as counting degrees of freedom and degrees of restraint.
Okay.
But I'm not very fond of this way of analyzing structures because, as I said during the course, there are cases where this is misleading.
But sometimes it doesn't work.
How do you count in this case? So for those of you at home, Elise asked me why I didn't count degrees of freedom and degrees of restraints. I didn't count them not because it doesn't work in the case of reinforced concrete beams, but because generally there are cases where it doesn't work. And to prove this, this is the structure. How many degrees of freedom do we have?
The roller is 1.
No, degrees of freedom.
3.
3.
So it's 1 beam.
So 1 beam, DOF meaning degrees of freedom. How many degrees of restraint do we have? roller, 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 1, 2, 3 equal to 3 degrees of restraint. What is the conclusion from this? Is the structure statically determinate? One would conclude it is statically determinate. Tell me.
I was just gonna answer no, because it's all in order, so it's a horizontal.
Yeah, I mean, clearly this is a structure which does not have the possibility of equilibrating forces in the horizontal direction. So if you put a horizontal load, the structure will travel. You will not write equations in the domain of statics. You will write them in the domain of dynamics. So F equal to m times a, where m is the mass and a is the acceleration. So you will determine an acceleration of the structure. Whereas in the vertical direction, it looks basically like this one. So if you put the load, you will need to solve the structure with a compliance equation. So, do such structures exist? Clearly, lorries, trucks, if they have more than 2 sets of wheels and an axle running through them, for sure they can travel in the horizontal direction, but when you load them, they will not fail. They will be able to support the loads. So that is why I don't like too much counting degrees of freedom. Although, again, I will underline it, in the case of continuous reinforced concrete beams, considering that I never give you such structures at the exam because you're not able to solve them, okay? In this case, it works. It clearly works. It's too cold. Ah, okay. I keep the window open. You tell me if it's getting too cold, okay? So having clarified this aspect, which is in my opinion important, I prefer the easy way. So it's a simply supported beam where you add one additional restraint, means one time unknown. Okay? How do we solve it? Guide me through the, or follow me. So the first case to solve the structure that you have to consider is basically the unknown force, the unknown internal force with value 1. Once again, why value 1? Because traditionally the coefficients we use for working out the deformations are given for unit forces and unit moments. So capital X equal to 1. LEJ, or I will not write it again. P, sorry, I went automatically, but it's not. In this case, no load applied. We just consider X equal to 1, basically meaning we consider P equal to 0. So if you have a bending moment, a unit bending moment at the center support, what you have is a deformed shape which looks like this. It is not symmetric. As you know, the rotation where the bending moment is applied is larger than the other one. What are the values? Well, standard coefficient, if you have a length L and the bending stiffness EJ, the rotation at the point where the bending moment is applied, so this rotation is L divided by 3EJ. Okay? And this, I mean, I don't request you to learn it by heart. It's given during the written exam. You have design aids where this standard coefficient is given. The rotation at this second point is L divided by 6EJ, just to remind you about the value, but I will put it between brackets. Why? Because in this case, strictly speaking, we are not interested in knowing this rotation. Okay? We don't need it to write compliance equation. Since we introduced the unknown force here, we are only interested in what happens here. Okay? Second span, it's L, 2L, sorry, and 2EJ. So we have to introduce the correct length and the correct bending stiffness in the standard coefficient. How do we do that? Well, basically here you have a rotation which is what? If this is the coefficient when the length is L and the bending stiffness is EJ, when you have 2L and 2EJ, basically you have 2L, so the length, divided by 3 times 2EJ. So the coefficient happens to be the same to the left and to the right, but this is basically because I chose to have 2L here and 2EJ here. So it's not a general thing, just happens in this case. Again, same considerations here. Rotation will be half this one, but I'm not going to write it for the same reason I put this between brackets. We don't need it. Okay? So what is the coefficient we need? Again, we know we can write the compliance equation in terms of rotation to the left is equal to rotation to the right, or we can simply look at the global relative rotation between the left and the right, which implies that I basically have to sum the counterclockwise rotation at the left of the support with the clockwise rotation at the right of the support, leading to a coefficient which is basically, I will again introduce the subscript just for similarity with what I did before, L divided by 3EJ plus L divided by 3EJ equal 2L divided by 3EJ, meaning the global rotation, the variation of the angle between the two spans at the center support. It starts from 180 degrees. The variation, this is an angle variation, is this one. Second case, only P with x equal 0. So, hinge, span, another span, load is applied here. This is P. Hi there.
Hi, Professor.
Do you have the notes of the first practical class we did, maybe? So you can look up the standard coefficient for which coefficient do we need? Of course, simply supported beam with distributed load. Clearly, the form shape is something like this, symmetric. So this rotation will be the same as this rotation. How much is this angle? In the case, this rotation, in the case of the standard beam, meaning by standard L and EJ, you will remember it's PL to the power of 3 divided by 24 EJ. Either you remember it or you have it in the design aid. In this case, clearly, we have a span which is 2L, so I will put 2L as the length, which goes to the power of 3, divided by 24 times 2ej, equal to, so 2 to the power of 3 is 8, divided by 48 means I'm left with PL to the power of 3 divided by 6ej. Okay? And this is all I need. Clearly, same rotation takes place here, but I will put it between brackets again, because it will not contribute to the compliance equation that I need to solve. So I can put here an equal and say delta 1, 0, thereby meaning the variation of the angle between the two beams, global. So the sum, which is not a sum because here we have 0, so it's basically 0 plus this one, so just this one. Variation of the angle between the two beams at the center support. Okay? So solution is very straightforward. Since the rotation or the variation of the angle between the two beams at the center support for capital X equal to 1 is 2L divided by 3ej, knowing that in reality the unknown bending moment is not 1, it is X, capital X, unknown value, capital X times 2L divided by 3ej plus PL to the power of 3 divided by 6ej should be equal to 0. Which gives you linear equation. So X is equal to what? Minus PL to the power of 3 divided by 6ej multiplied by 3ej divided by 2L. So what I'm left with is 3 goes away with 6. Here the 2 remains. Ej cancels out. 1L cancels out. Minus PL to the power of 2 divided by 4. Got it? Simple math. Don't mess it up when you do the written exam. I told you before, it's not that if you mess up the calculations you get 0, but to decrease the points available just because you miss or you mess with calculation like this is stupid, okay? Are we good so far? If you remember the first practical class that I gave, we had a structure which looked more complicated, but by using symmetry, by taking advantage of symmetry, it was simplified. In this case, structure is not symmetric, but it has only one unknown. So, generally speaking, calculations are quite simple. Besides, if you use the calculator, in the most general case where you have two unknowns, so you have to solve a system, there are calculators that solve systems of equations. So check the instructions of your calculator, you may be able to solve it with the calculator. I mean, again, this is not a math exam. I don't care how you solve the systems of equation, I just care that the results are right. Okay? And by saying I don't care how you solve the calculations, the only thing I care about is that you solve them by yourself, okay? Is this correct or not? Is this result correct or not? Let's give it a check. How? I'm going to calculate the rotations to the left and to the right of the center support. So, to the left. Can you please pick a convention? I am now calculating the rotation at the left of the center support. Do you want it clockwise or counterclockwise? Yes. It's just to show that convention is totally arbitrary.
To the left of the
Center support, yes.
negative.
Negative doesn't mean anything. You have to tell me clockwise or counterclockwise. Counterclockwise, okay. So, I'm going to calculate the rotation to the left, assuming it to be counterclockwise, meaning like this, okay? What is the first contribution to the rotation to the left? It's L divided by 3EJ in the case where the unknown internal moment is 1. Okay? It is, as a matter of fact, counterclockwise. So I'm simply going to write x multiplied by L divided by 3EJ. Okay? As for the distributed load, there is no rotation to the left of the center support. Therefore, I could write here, just for the sake of clarity, plus 0, no contribution from distributed load and so I can do the calculation. What is the value of x? Minus PL squared divided by 4. Times L divided by 3EJ. So what would the result be? It would be minus PL to the power of 3 divided by 12EJ. How do I interpret this result? She picked counterclockwise rotation. I substitute the value which I obtained for capital X and I get a negative value. What does this mean? It means that if I have a counterclockwise negative rotation, it is in reality clockwise. So this minus sign here, together with this assumption, means rotation is clockwise. Is it right or no?
Yes.
Manit. Could we have guessed in the beginning?
Yes.
Who plotted this deformed shape? Rotation is clockwise. I know you like conventions, so pick the convention for the rotation to the right. Clockwise or counterclockwise?
I always like clockwise.
Let's do it clockwise, but since we now know how the smoke goes around, as we say in Italy, which means we already know what's coming, okay? Tell me, what result do you expect? Positive?
Anti-clockwise.
Sorry, you're right. I'm not familiar with watches anymore because I always look at the time on the phone. So, what do we expect? Do we expect a positive value in the end or a negative value? Positive. So, this is what you were going to say. Yeah, but feel free to speak up. I mean, there are so little of us. No problem. It's informal anyway. Yeah. So if we get a positive result, it means the rotation is indeed clockwise. And since we already know what the deformed shape looks like, we should expect a positive value. Let's do it. First contribution is L divided by 3 EJ when the capital X is set equal to 1. Meaning that the clockwise rotation, it is indeed clockwise, as you see here, is X times L divided by 3 EJ. For the distributed load, we have a clockwise rotation, which is PL to the power of 3 divided by 6 EJ. So we'll put a plus here. Again, I will not redo the calculations. This is basically the same as this. So the result is minus PL to the power of 3 divided by 12 EJ plus PL to the power of 3 divided by 6 EJ. The result will be PL to the power of 3 divided by 12 EJ. Clockwise, as should be expected, as we expected. Not only this value is exactly the same as this one, meaning the two spans rotate by the same amount. So results look good. As a matter of fact, if you look at this and you take into account that this is counterclockwise and this is clockwise, and you make this term equal to this term with the minus sign, you get this equation here. Okay? So writing this equation, or writing this, and putting them equal, provided the convention is the same, is exactly the same thing. No wonder. Of course, we can use, we can calculate rotations also in other points. I said we have this value here, L divided by 6 EJ, and I put it between brackets because I said we don't need it for the compliance equations. But suppose we want to check again the result. So suppose we want to know what the rotation of the first support is, okay? How do we calculate it? I'm going to write it here just to save space. Elise, how do we expect the sign of the first rotation, so the rotation at point A to B? Clockwise or counterclockwise? Yes. We expect it to be counterclockwise. So again, this way. How is the rotation due at the first support due to x equal to 1? It's clockwise equal to L divided by 6 EJ. So if I'm writing a clockwise rotation, a counterclockwise rotation, I have to put a minus sign, have to put x, then multiply by L divided by 6 EJ. The result is quite obvious. It will be PL to the power of 3 divided by 24 EJ. It is positive, meaning it's counterclockwise, as was expected over there. Okay? That's how you can use coefficients which are not directly used in the compliance equations. You can use them with superposition principle to calculate whatever quantity you want. For example, if I solve this beam, okay, I may be interested in writing the compliance equation somewhere, provided that this is statically determinate, but then I may want to know the displacement there. Why the displacement there? Because we have this wall, and if this beam deflects too much, it will damage the wall. There are also lamps and things like that attached. So the displacement over there is a crucial point. I don't want my structure or my non-structural portions to be damaged. So after solving the whole structure, I may want to calculate the displacement over there. Here it's the same. If I have something strange happening in the first support, after I solve the structure, I can get the rotation of the first support. Okay? Yes, tell me.
Here on standardization, when we assumed it was counterclockwise and we got a negative result and said it's clockwise, which one are you talking about? On the left of the
Support B.
But is it anti-clockwise?
There it was counterclockwise.
Yeah.
Yes, but we got a negative value, which means it's clockwise.
Oh, which means we drew it wrong.
Hmm?
Which means we drew it incorrectly.
Yeah,
Okay.
basically yes. As a matter of fact, you realize it's not that it's wrong. It is consistent with the bending moment we assumed, which is positive, but we got a negative value, and therefore everything is reversed.
Which means the bending moment is actually negative.
Hmm?
Which means the bending moment there is actually negative.
It is.
Oh.
We found it. Okay, so basically we solved the structure. Now let's solve the different parts just to get all we need to go into drawing the bending moment diagram and calculate the reaction forces and also draw the shear force diagram. So we have basically two spans, 1 and 2. This length is L. This is 2L. I'm not writing the bending stiffness because when I go into equilibrium equations, I don't need this bending stiffness. Tell me.
Not really clear. The last one, rotation at the first one.
The first support,
At
yes.
the first support, counterclockwise.
A, yes.
And then we put minus x.
So it's not clear why I put the minus.
Because of the rotation of the
And now I erased, but the thing is, the rotation of the first support for X was clockwise, okay? Okay? If I want the counterclockwise rotation, I have to put a minus.
No, I'm just
You have to think about it. It's basically the core of the sign convention. If I tell you I have an upward force of -5, it means it's a downward force. Okay? So a clockwise rotation equal to delta is a counterclockwise rotation equal to minus delta. Okay? So I split the structure into the two spans, and now I'm going to put the bending moment, which I found, and find out the reactions or the shear forces at the ends of the beam. So we have PL square divided by 4 here, and PL square divided by 4 here. And now I don't need to put signs. I mean, it's positive because I plot the arrows in the correct direction. Okay? So negative bending moment. As usual, I have here what I call VAB, and here what I call VBA. Here I will have something which is called VBC, and here I have something which I call VCB. The convention for the subscripts was explained during the first practical class. Both shear forces refer to the span BC or CB, it's the same, but if I put B in front, it means I'm looking at the shear force at point B. Okay? What would the equations be? Well, first I can start by writing a rotation equilibrium about point A of AB equal to 0, which gives what? With respect to this point, we have PL squared divided by 4, which is clockwise, VBA times L, which is counterclockwise. So basically we have VBA times L minus PL squared divided by 4 equals 0. L cancels out. And what you're left with is VBA equal to PL divided by 4. Okay? Basic equilibrium equation, rotation equilibrium. Second equation could be M with respect to B of the same span, or it can be Ry equal to 0. So translation in the vertical direction equal to 0. Ry equal to 0 is basically VAB plus VBA equal 0. So VAB is basically minus PL divided by 4. What is the meaning again of the signs? And you tell me. Okay? So here, I assume VBA to be upwards and VBA is a positive value. What does that mean?
It's right.
It's correct. I mean, I can simply go here, cancel this, and write PL divided by 4. So my guess on the direction was right. And if I get the negative value here, what does it mean?
Then it goes down.
That it goes downwards. So I can replace this by this. And you can pretty much see what this leads to. We have a bending moment which goes clockwise, and which is counteracted by a couple of forces which go counterclockwise. Okay? Can you see the effect of two forces apart in this? They generate a counterclockwise rotation which is counteracted by the bending moment. And this span is in equilibrium. Okay? For the second span, you simply have to remember that there is a load, P, whose resultant is P times the span, so P times 2L, placed where? In the middle. So this is 2PL. What would the two shear forces be? Again, M with respect to B of BC equals 0. What do I have? Careful, careful, careful. Even if I'm at point B, where the bending moment is applied, I still have to take it into account, okay? Make no mistake about it, okay? It's not like with forces. With forces, if the force passes through the point which you use to write the equilibrium equation, it does not count because it has a zero lever arm. For the moment, this does not apply. So even if PL squared divided by 4 is applied here, it counts. And we're going to start with that. So it's PL squared divided by 4, which is clearly counterclockwise. Then we have minus 2PL times L, which is the contribution of the external load. So minus 2PL squared, which is clockwise. And then we have CB, VCB, which is like this bending moment, counterclockwise. So plus 2L equal 0. What would the result be? This minus this is 7 divided by 4, I would say. divided by 2, it becomes 7 divided by 8. Okay? So BCB okay? And then Ry equal to 0 basically means that VBC is equal to 2PL, the applied load, which goes downwards, minus 7 divided by 8PL. So 2 minus 7 is 9 over 8. Okay? Sum of the two forces is 9 plus 7, 16 divided by 8 is 2PL. So it's equal to the applied load. Doubts about that? Questions? You on the back? You okay with that? Reaction forces. Let's look over there. So at point A, we have a horizontal force and a vertical force, but the horizontal force is clearly 0. It's the only horizontal force acting on a structure which has no loads in the horizontal direction, so basically equal to 0. So HA is equal to 0. What about VA, the reaction force at the first support? VA can be seen over there. It's basically the shear force at the left of span AB. PL divided by 4. And to make it clear, I can simply write PL divided by 4 and say downward. Or as some of you do, I mark it like this, just to specify the sign. Let's go to C. At C, the shear force is VCB, and this is equal to the reaction force. Remember, like we said last time, at the end of the beams, basically the shear force coincides with the reaction force. Or if you want, the reaction force resurfaces on the structure as shear force. So at point C, very easy, 7 divided by 8 PL upwards. Okay? Now, what happens at point B? There you have to be careful, and maybe looking over there helps us to understand that this force and this force, they are the result of the reaction force. So the reaction force is basically the sum of the two, which then subdivides part to the left and part to the right. So at point B, the reaction force, and look at the symbol, is VB, is VBC plus, I called it, I think, VBA. And what is it? It's clearly 9 divided by 8 plus 2 divided by 8, because PL divided by 4 is 2 divided by 8. So the final result is 11 divided by 8 PL upwards. Doubts about this? No. Okay? No doubts whatsoever. Let's do a quick check. 11 plus 7 is 18 divided by 8. Minus PL divided by 4, because this is upwards, this is upwards, this is downwards. So 18 divided by 8 minus PL divided by 4, which is 2 divided by 8, is 16 divided by 8. Again, the sum of these three reaction forces is exactly equal to 2 PL, which is the load applied, as should be expected. But again, as I told you multiple times, if you get the value of X, capital X wrong, you can still get equilibrium in the vertical direction. Because there are infinite equilibrated solutions, only one that is respectful of compliance also. If you miss that one, you can still have equilibrium, but with wrong forces. Okay? Now, some of you may ask me, why do you spend so much time on structural analysis, which is basically the first part? Well, not that I have to justify myself. I'm the professor, so I can do whatever I want, but from the first written exams that I corrected during the winter call, I saw that most of you have more difficulties with the structural analysis. The design part is usually better. So I'm trying to stress these basic concepts, also because I think the structural analysis is the core for understanding basically conceptual design. And if we had more time, we could also elaborate more on that. But credits are what they are, and the related time is what it is. So, okay? So let's plot the shear force diagram, V. My convention is shear is positive if it is clockwise. So I have two spans, one, and the second, which is double the length. No equations. I know Maria Chiara did it with equations. If you want, you can look up the equations, but I would like to do it in a more intuitive way, okay? So let's first look at this one. Here the shear is clearly, we are at the left end and it's downwards. If you see my square over there, at the left end, positive means upwards. So this for me is a negative shear. Same considerations apply for this. So basically, with my conventions, shear is positive if it induces a clockwise rotation. The whole first span is subjected to a negative shear force, which is constant because we go from PL divided by 4 negative to PL divided by 4 negative, okay? Make no mistake about it. You don't have to look the direction. You have to compare what happens here and over there to the small square I have drawn over there. Minus PL divided by 4. In this way, it is clear. This is everything I need to see. The fact that I write the value with the sign inside the rectangle clarifies that the value is constant. Otherwise, I would have written a value here and a value here. Okay? What happens in the second span? At the first point, which is again to the left of the beam, upward force, which means positive. Okay? So first value is positive and it is equal to 9 divided by 8. This is 2 divided by 8. 9 divided by 8 means 4 times this segment. I will not draw it in scale, otherwise it becomes too big. Okay? So I'm going to start with a positive value, which is 9 divided by 8 PL. First value. Okay? Second point, where we have VCB, you can see VCB points upwards, whereas in my convention, to the right hand, positive means downwards. This implies that VCB for me is a negative shear value. It's 7 divided by 8, so it's smaller than this one. A little bit smaller, just a little bit smaller. 7 divided by 8 PL, and to make it clear, I will then put the sign, but I will put it inside the graph. What happens in between? Yes, straight line, linear shear force diagram from the first point to the other.
In the middle.
What in the middle?
2 p.m.
No, it's distributed.
No, I just want to say it goes to the middle now.
No, 0, the 0 value.
There and cross the beam.
So, okay, let's first plot it and then we're going to elaborate. This is what the shear force diagram looks like. This is a positive shear force portion. This is a negative shear force portion. The point where the shear force is 0 is not the middle, because the shear force here and here are different. So it's moved, okay? Basic concept, because you will then need it to calculate maximum bending moment.
Why VBA? So VBA was positive PL over 4, but on the diagram it's a negative.
Because my convention is this one for the shear force.
It's not.
You have to be aware of the fact that when I fix conventions here, it's just because I want to know the sign and the direction of the forces. The moment I know the sign and I mark the arrow in the right direction, my convention is gone. For example, at this point, I marked an upward arrow. As soon as I got a negative value, I deleted the arrow and I simply replaced it with the correct direction. So my convention is gone. I don't care anymore that this was negative and this was positive. The important thing is physics. So this is upward, this is downwards. That's all I need to know. Where will this 0 point of the shear force be? Not going through all the passages, but let me just remind you that the shear force as a function of x, where x is this coordinate. So from the center support to the right on the second beam is 9 divided by 8 PL minus the value of the distributed load, which is P times X. So where is the shear force 0? Question mark. Where N divided by 8 PL minus PX is equal to 0. This happens when X is equal to 9/8L. So just slightly to the right of midspan, which means in turn that this segment here is 7 divided by 8L. Sum of the two clearly gives you 12, which is the length of the span. Once more, let me point out, we did it before, but what is the discontinuity here? What is the difference between this point, which is positive, and this point, PL divided by 4, which is negative? This value here of discontinuity is 11 divided by 8 PL, which is equal to RB. So again, the presence of a concentrated load in the form of reaction force, in this case, marks a discontinuity in the shear force diagram. Got it? This looks pretty much like what we did in the first practical class and also what we did in the last class. You tired?
No, just,
Come on, it's Thursday. Week is almost over.
yeah. I have class on Saturday.
That's not possible. That violates civil rights of students.
No one cares about our rights. So my week is not almost over. But anyway, I have a question. Is this the same with, like, we can also do it by doing, like using the moment equation, right? Okay. Like moment about a certain point.
Never thought about it. It gets probably more complicated.
That's how.
Why do you need a moment equation?
Because the question is at, like, you take, what is the distance at which?
The shear force is 0.
Yeah, exactly.
Yeah, but we are talking about shear force.
So where did we get this expression from?
This,
Yeah.
from here, starting from the left going right, and writing equilibrium equation on a small portion of beam. This is basically what Maria Chiara usually does, what we did last time, so this time I made it a little bit quicker. But it's basically like this. Point B, have the shear force 98 PL, you have the load which is P, this is X, and this is V, okay? So you can work out V as a function of X all along the second span. And this is the equation which comes from this. And by asking yourself where the shear force is 0, you get this length, which is this. Bending moment diagram, M. My convention is I draw the bending moment diagram on the tension side, okay? Which means by specifying it in front, I don't have to mark positive, negative. I just have to look at values and plotting the diagram on the right side. Here, as you see, I plotted the negative shear force values below the beam, here and here, the positive above the beam. This convention is okay. You can also use another one, provided you're consistent. So don't plot both the positive and the negative values on the same side of the beam, okay? Be consistent. What is the moment at the first point? Point A, it's 0. What is the moment at the last point, C? It's 0. What is the moment at the intermediate point? It's PL squared divided by 4. It's negative, so tension is at the top. So here is my point. These are the 3 points of bending moment known that I have so far. Okay? What can I plot with just these 3 points? Well, in the first span, where there is no distributed load applied, I know that the bending moment diagram will be a straight line, so it will be linear. So 2 points are enough. This is what the bending moment diagram looks like. No doubt about it, consistent with what we guessed at the beginning. Look at the arrows over there. I said from the beginning, taking advantage of the deformed shape plotted by your colleague, that the bending moment was expected to be negative. Here, on the second span, as usual, when we have a distributed load, we expect the bending moment to be parabolic. And as I said during the first practical class, if you have to draw a parabola, 2 points are not enough, because through 2 points, there we have infinite possible parabolic shapes, okay? It's like if you have 2 points, there is only one straight line which passes through the 2 points. If you have just 1 point, there are infinite straight lines, okay? With a parabola, it's the same, with number of points increased by 1, okay? That comes again from mathematics. So we need a third point. And what would the third point be, as usual?
The 0 point in the shear.
Speak out. The point?
The 0.
What's your name?
Daniel.
Daniel. Why the point where the shear force is 0?
It represents the maximum end of the moment.
The maximum?
The maximum moment in this section.
Yeah. It's the point of maximum bending moment. Yeah. I'm going to calculate it here, but then I will delete it because I want to go with the deformed shape just below, okay? So suggestion of Daniel is calculate the bending moment at the point where the shear force is 0. That's basically why I worked out this one. I knew it from before. It's the point where we expect the maximum, we expect the bending moment to be maximum, okay? Relative maximum, not the highest value, but a point where first it increases and then it decreases. So it's a relevant point, it's a significant point. So what do I do? Well, basically, I know the shear force is 0 at 7 divided by 8L from the right. So I take a portion of beam, which is 7 divided by 8L. I know that to the right, we have a reaction force, which is 7 divided by 8PL. I know there is a distributed load, which is P, and whose resultant force on this small portion of beam is how much? 7 divided by 8PL. You can see that there is a certain pattern, okay? 7 divided by 8PL, 7 divided by 8PL, 7 divided by 8L. This simplifies the equation. Is it a coincidence that here we have 7 divided by 8PL and here we have 7 divided by 8PL? Or does it happen every time that I do this? No. You think no? Daniel?
It's because it's the same. If the distance for the load is going to be the...
No, more intuitive. It's too complicated for me. Of course, it is always this way. We broke where the shear force is 0. Therefore, this has to balance out this one. It happens all the time. So, R moment is M maximum. What is the equation for M maximum? Well, this is taken as positive, clockwise, plus the contribution of the external load, which is 7 divided by 8PL, acting over with a lever arm, which is 7 divided by 16, because it's half the total length. So it's this plus 7 divided by 8PL times 7 divided by 16L. And then we have the contribution of the shear force, which is 7 divided by 8PL, and whose lever arm is 7 divided by 8L, equal 0. This is all we need. So basically, we have to take 7 divided by 8 to the power 2 divided by 2. But that's the result of this calculation. So it would be 49 over 64 divided by 2, 49 over 128. That's the final result. You can check it out, but I'm quite confident that it's correct. It always happens like this. Okay? That's the third point we need, and then we can draw the parabola. Let's have an idea. So this value is PL squared divided by 4, which is 0.25. This is 49 by over 128. I think it's more than 0.25, clearly. It's almost half. 49 is almost half of 128, which is half of 128 is 64. So we will have a larger positive bending moment than negative bending moment. If you have written down this, I will cancel it out. So I have room for drawing the bending moment diagram and then the deformed shape. How much is 49 divided by 128? .038 divided by 0.25. Basically, the positive bending moment, the maximum positive bending moment is 1.5 times the negative bending moment. So this means take this segment, 1, and then it's half. This will be the maximum value, and the parabola looks like this. Okay? And now we go back from where we started by plotting the deformed shape. The notable points, besides the supports, where we know displacement has to be 0, at the center support continuity of rotation is a must. Last notable point is the point where the bending moment is 0, because we expect there a point of contraflexure, which means a change in curvature. Putting all of this together, a possible deformed shape, a likely deformed shape looks like this. Here, curvature looks like this. Here, curvature looks like this. Here, you can see the change in sign of the curvature. And as we said at the beginning, since there can be no abrupt change of curvature, there is a small portion of the second span where the bending moment is negative, okay? As you see, the bending moment diagram does not have the jump the shear force diagram has. Okay? Yeah.
Can you?
I can.
I want to do this. Thank you. So remember when you said here, if we always have that pattern with the where the shear always has to be equal to the load because
It was down there, but okay.
I mean this. Oh, you erased it.
Yes.
Okay. Anyway, can we also say the same thing that the tier x will always be equal to
This without the
divided by
P,
the load?
if the load is P, yes.
So this divided by the load, whatever. Yeah?
Yes. If you start from the left. If you start from the right, it's the other one divided by P.
Other one as in this one?
No, here. If you start from the left, it's 9 divided by 8. If you start from the right, it's 7 divided by 8.
No.
And the same rule applies. Reaction force, you take away with the load.
Yeah, I'm gonna
It's
need
basically a thing about proportions.
Okay. Thank you.
Talete's theorem, okay?
What is it called?
Teorema di Talete. I mean, you know, this to this is like this to this. How do you call it? Hmm?
Is it the same as similar triangles?
Yeah, I don't know how it's called. In Italian, I think it's called the Teorema di Talete. When you have something like this,
Yeah, I think we call them something else.
this is to this, like 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 this is to this. It probably also has to do with what we call a similitude dei triangoli. About triangles, yes. But I think it's Teorema di Talete. I don't remember. So we keep the upper blackboard because there are values which we need for solving the structure. Now we go to the design tasks, which you will see are a piece of cake compared to structural analysis.
Sorry, could you please explain why it's a straight line from A to B? Why is it a straight line from A to B? Could you please explain that?
Well, I could get it with equations,
Mm-hmm.
the way Maria Chiara does it, and the way you have in the notes that Maria Chiara did and we uploaded on Weebit. But basically, if you have a beam which is unloaded, okay, the bending moment is a straight line.
Okay. So when
If you're not convinced, I mean, you can do what I did there for the bending moment and you will get the same result. Let's just quickly do it. Suppose I'm focusing on a small portion of the beam starting from the left, okay? It will be what? Subjected to the left to PL divided by 4, and here I assume my bending moment M like this, okay? To keep this small portion which has a length which is X in equilibrium, what bending moment is required? M rotates clockwise, PL divided by 4 rotates counterclockwise and has a lever arm of X. So to keep this in equilibrium, M should be equal to PL divided by 4 times X. And if you have such an equation, this is the equation of a straight line. Okay? The further you go from the first end, the larger becomes the bending moment in proportion to the length. Okay? If you are at midspan, okay, here, L divided by 2, you have PL squared divided by 8. If you go here, PL squared divided by 4, okay? It's a straight line.
So between B and C, if it was a point load instead of a distributed load, the moment, the bending moment was still here.
Would be 2 straight lines, but this we will cover in further practical classes. So then some numerical values were given, but basically the first task was design the longitudinal reinforcement at the bottom of the section at the point of maximum, and then between brackets, positive bending moment, assuming 16 millimeter diameter rebars. So basically, we are talking about rectangular section with reinforcement at the top, more reinforcement at the bottom, stirrups enveloping the longitudinal bars. The data given were the effective depth, so the distance between the bottom reinforcement and the top fiber. D is equal to 35 centimeters. We also have FYD, which is the design yield strength, which is 380 MPa. So basically, we are designing the bottom reinforcement at a section where you have a bending moment which is like this. M, okay, positive, consistent with what we got over there. What is the maximum value of positive bending moment? We just worked it out. I then erased it. It's 49 divided by 128 PL square. The data were, in addition, P equal to 15 kilonewton over meter, L is equal to 5 meter. So let me do the math. Times P, which is 15, times 5 times 5, 144 kilonewton meter. Okay? Something like what we saw last time with steel. Okay? Careful with the units of measure. Usually when we have bending moment, we express them for ordinary structural members in kilonewton meters. If you go into bridges and things like that, you may want to use other units of measure, but kilonewton meter are okay if you work with beams. Okay? So, what would the resisting mechanism be in such a beam? We know it. Some compression forces in the top of the section where there is concrete and steel. At the bottom of the section where you have cracks, so you will expect some cracks to take place where the section is in tension. There is only the tension force in the bottom steel. And the stress in the steel is FYD. So once again, as usual, we have a compression force in concrete plus steel, a tension force which is FYD times AS, where AS is the total number of rebars at the bottom. So the sum of these rebars is AS. Okay? Distance between these two forces is called internal lever arm. We can calculate it. It's 0.9 point D, where D is the effective depth, which is 35. So 0.9 times 35 is equal to what? Again, the calculation. (31.5 centimeters). And then you can simply take into consideration that since the bending moment is resisted by this force and this force, we can simply say M equal to FYD times AS times Z, which, rearranging the equations by working out the only unknown we have, which is AS, gives us this powerful design equation. M applied divided FYD times Z. Replacing the numbers and being careful with the units of measure. So the area we are going to determine is an area of steel. You can use either square centimeters or square millimeters. It's the same. I prefer to use square millimeters, which means that I have to transform every meter into millimeter. And then since this FYD is given in megapascals, which are, once again, Newton over square millimeters, I'm going to transform everything into newtons. So what we have in the end is M is 144 times kilonewton meters. So kilonewtons are 1,000 newtons, meters are 1,000 millimeters, meaning I have to multiply the bending moment by 1 million, which is 10 to the power of 6. Okay? Everything then, FYD stays the same, 380. The internal lever arm, which I have here in centimeters, will be transformed into millimeters. So instead of 31.5, 315. $144 times 1 million divided by 380 divided by 315, 1,203 square millimeters. Okay? What is the area of a single 16 millimeter rebar? I should learn by heart by now, but I should have learned by heart at this point of my career, but I did not. No, it's probably 200. Sorry?
Pi b squared.
Yeah, it's clearly P times the diameter to the square divided by 4. So it's P times 16 divided by 4, which is basically equal to something like 201 square millimeters. Which means this and this together, number of rebars is what? 1,203 divided by 201. It's probably something between 5 and 6. Not exactly 6. 598, which means almost 6. So by putting 6, I'm probably safe enough. In any case, safety is covered by the coefficients we use. So the fact that, for example, here you have a FYD, which is much lower than what the steel can sustain. And here you have a load, which is not visible from here. It will be a higher load than what is the surface load. Questions about this? Any questions about this? Everything okay? The second point said, design the longitudinal reinforcement at the top of the section at the point of minimum negative bending moment, assuming 16 millimeter diameter rebars. Now, if you agree, I will skip this one. It's basically the same, upside down, okay? The difference is there is a different bending moment. Okay, you use PL squared divided by 4 instead of 49 over 128 PL squared. The effective depth was slightly larger, so 37, but that's about it, okay? It's not interesting. It's basically the same calculation. Let's go to the third point, which is more interesting. It said, determine the spacing of the stirrups required at the third support, point C, assuming that the stirrup consists of two-legged vertical 8 millimeter diameter bars. Okay, this is probably more interesting. So we are at the point C, meaning We are at the far right end of the beam where we know there is a reaction force or shear force. We called it VC or VBC or no, VCB. So VC equal to VCB, 7 divided by 8 PL. What is the value? 7 divided by 8 times 15 times 5. 65.625, let's make it 66 kilonewtons. Okay? Again, when we have this, we have to remember we consider a sort of truss mechanism consisting of a bottom chord, inclined 45, like this, and we consider it to be continuous, so we imagine there is a continuous flow of forces like this, and this is how we determine the tension force in the vertical members, which are then the stirrups we consider. To go back to the theory that gives us the equations we use, the formulae we use, look at the notes which were provided to you. One important thing is to know of the truss, the distance between the two chords, the top chord and the bottom chord, which is basically Z. Again, internal lever arm. At point C, we are in an area where there is positive bending moment, as you see from the diagram above. So this zeta, this Z is basically the 315 millimeters we had used before. Okay?
Professor,
Yeah.
if it's a support, doesn't that mean that traction would be on the top? Or does that only work for the intermediate supports?
Depends on the bending moment diagram. We have three types of support. We have an end support where the bending moment is 0 or 0 becoming negative. Another support where we have it 0 becoming positive, and the support where it is negative. So, depends. You have to look at the bending moment diagram. Always.
Okay.
Or, more correctly, you have to look at whether the bending moment increases or decreases, moving, in this case, from the right to the left. Okay?
Is it always increasing from a support to somewhere else?
Why do we always want general rules? There are no general rules. Every structures are like human beings. Okay? Every structure has its own peculiarities. Going into the characteristics of the structure means solving equations, plotting diagrams, and then looking at the diagrams, you know basically everything you need to know. So, for example, regarding the crack pattern, which will take place in this beam, I can understand by looking at the bending moment diagram. I know there will be cracks at the top where the bending moment is negative. I know there will be cracks at the bottom where the bending moment is positive, okay? And the more I go towards the supports, the more the cracks will be inclined, okay? Because the shear prevails. That's all you need to know. There are no general rules, really. Besides, always remember this. I introduced differences in the effective depth for areas of positive and negative bending moment because I want you to be aware and to understand the concept of positive and bending moment. But the difference between 35 and 37 basically plays no role, okay? So I'm just specifying this to introduce some more concepts, but it's not what makes the difference. What makes the difference is that you understand how the truss works, okay? Then if this is 35 or 31 or 32 or 33 does not make a difference, okay? Got it?
Professor, where?
Because, for example, sorry, in this beam, if you are at the first support and you move to the right, the bending moment decreases because it becomes more and more negative, okay? If you are at the right support and you go to the left, the bending moment increases because it becomes more and more positive.
But you're not talking about value, are you?
No, I'm talking about increments.
Okay. And don't we care about value?
It would be better to care about the increase, but this is not a concept we introduced, so I try to make it simple, just to simplify stuff for you.
So I can't just assume that tension is always at the top on a support.
That definitely not.
Okay.
But that you see from the bending moment, not from the increase.
Yeah.
Tell me, Daniel.
That is 66, it's coming from kilometers. I don't understand what is this number.
The load is 15.
Okay.
These were the data.
Okay.
Now, for the shear force, we know ASW is equal to what? V times S divided by FYD times Z. I don't know if I wrote the formula in this way. I don't know if I wrote it the other way around. One way also to express it is ASW divided by S is equal to V divided by FYD times Z, okay? Whereby this is the spacing of the stirrups. So, if stirrups are like this, S is the spacing. ASW, number of legs of the stirrups times the area of the stirrups. So this I know because it was written clearly. Two-legged, so number of legs is 2. Diameter is 8, so I can replace 2 times P times 8 to the power of 2 divided by 4. A result of this is probably about 100 square millimeters. Okay? If I rework this equation, basically what I get is S is equal to what? FYD times Z divided by, hope I didn't mess it up, ASW divided by V. Let's do this quick calculation. 380 times Z is 315 times the area is 100 divided by 66,000 because I have to use newtons. Result is 181 millimeters, 18 centimeters. Stirrup spacing, and it looks reasonable. C'è già il prof? No, ok, ho quasi finito, eh. Ok? Why longitudinal reinforcement, it is wise to round up, okay? I get 5.5 bars, I round it up to 6. In the case of stirrup spacing, it is wise to round down.
Because when you decrease the space, they close at each other, so more support.
More resistance, yes.
Question.
Yeah.
In real life, like when we're designing these, isn't there an issue though when you do too much reinforcement that weakens the concrete?
There is always a limit on the reinforcement that you put, also because of economic reasons. If you put too much reinforcement, it means your design is not feasible. I mean, if I get that half of my reinforced concrete section is made of steel, then the suggestion is then make the whole section with steel.
But that issue would never happen.
18 centimeters is reasonable. If you get 2 centimeters, then it's not feasible. I mean, you can go down to spacings like 5 centimeters, okay? In areas where the shear force is very high, or when you have columns which resist to lateral forces like in seismic areas. There you need the stirrups very close because they have to confine, they have also to make the concrete more ductile. But 18 centimeters is reasonable. Just one thing, clearly, people who put the stirrups in place, they don't like 18 centimeters, okay? So for example, if you round it down, then maybe round it down to 15, okay? Or one other trick is to give the number of stirrups instead of saying the spacing. So you say, for example, 1 meter from the first support, keep the stirrups at 15 centimeters, place 5 stirrups, place 7 stirrups, and then they count, and based on their judgment, they will put it. Yes,
for the contract.
Okay, but what do you think? That if I write 18, they will go there with the ruler and play 18, 18. The thing that may happen if you make like stirrup spacing is 18.5 centimeters is that the stirrup becomes your thigh, okay? Once you go to the working site.
No, I'm only saying that because, like, let's say in Canada, if I did something like that, and I said, "Oh, my joists for my floors are like I have 5 joists per beam between the beams." You can just go and stack them all on one side, and you won't care.
Yeah, I mean, but if the area where you place the stirrups is narrow, there is also less room for arbitrary choices. Besides, could be reasonable to assume that stirrups are placed at equal distance. But you're totally right. The more you put, the better it is. I'm just dubious about the fact that if you put a spacing like, suppose you want to place 3 stirrups in 1 meter, you should write 1 stirrup every 33 centimeters. Not measure it. On the contrary, if you say in 1 meter place 3 stirrups, or 4 stirrups, depending on how you look at it, it's different in my opinion. But you are right. But again, it's not that putting the clear indication makes you sure that then the stirrups are placed at the correct spacing, okay? Questions? People at home or online, whatever, wherever. Okay, I think the class was correctly recorded. I hope so. I will provide you the link as soon as I have worked on it, renamed it. And see you in 2 weeks. The week after Easter. So there will be some vacations. So I have some nice vacations. Weather should be better now. Can go outside. Okay.
Thank you.